And otherwise, we're all here, huh? Welcome back, those of you guys that were gone at the end of last week. Glad to see you. Hope the weekend afforded you the rest that you needed to kind of keep recuperating. I think this flu is on its way out. Praise the Lord. And I heard that, I think this weekend or the beginning of next week, we're supposed to get back up into the 80s, which is kind of nice. I don't really like the 90s and the 100s, but the 80s I don't mind. That'd be kind of nice. At least for some of us, huh? All right. Number 4, identity matrix. Number 8. You guys were setting up, I think there were equal matrices, right? So you were trying to find X and find Y from setting up the terms. Number 32 was a little weird in some ways, unless you realized I can just solve for X by adding the 4a and then dividing by 3 or multiplying by a third. So in that way, you were just multiplying matrix A by 4, multiplying matrix B by 2, and then multiplying by a third at the end. Some people might have left the third outside. Some people might have brought the third inside. But there's your final answer for that one. Number 44 was a matrix multiplication. So remind me, what are you supposed to do when, wait, how does it work? What is my left hand doing when I matrix multiply? Cross, good. And then what's my right hand doing? Down, perfect. When I'm pointing, what operation? Multiplication. And when I switch, what operation? Addition. So where did this 252 come from? 132 plus 60 plus mental mathers, 60. Good. 132 plus 60 plus 60 was that one right there. And then once you cross down, what do you do next? Cross over down. So then where does that 30 come from? It comes from 110 minus 144 plus 64. And once you finish the first row, first column, and first row, second column, then what do we do? Okay, good. Second row. Time to cross down and cross over down to get our 2. And then once we've done the second row, first column, second row, second column, third row. First column, third row, second column. Boom, boom, done. Why was it legal? Good. The number of columns, 3 columns, matched the number of rows, aka everything had a corresponding entry. Excellent job. Number 62. You might have gotten a little stuck, but the ironic thing is it actually took you back to section 8 point, do you see it? RREF. Took you back to section 8.1 to review. The directions might have been a little weird. You might have been a little bit stuck as far as how to start the problem. But once you realized it was a system of equations, all you had to do was make an augmented matrix and then RREF all the way down to get your identity matrix and 2, 3 halves, 3 halves as your final X equals Y equals Z equals, but they just wrote it in a matrix. That was what was a little different in section 8.2. They said, hey, the variable matrix, the things that you were missing at the very beginning, we can write it as a matrix, and that's fine, you can. In section 8.1, we would separate them with commas and put them in parentheses. Either way, they represent the solutions to the matrix. So if you guys need to, you can write yourself a little note. Maybe you got stuck with what you were supposed to do. The directions looked a little different, but what you were doing was going back to section 8.1, RREF row operations. Oh, that was the last one, huh? Okay. I do have my book open, I think, to section, oh, I'm sorry. I'm in chapter 9. That doesn't help you guys. Here we go. Section 8.2. Do you have any questions, evens or odds? Matthew.
How do you multiply the matrices? Like, how do you know which numbers to multiply by which when you...
Oh, this is something that we worked with a lot on Friday, so you might have not been able to fully develop since you weren't here. That might have been a little bit hard, Matthew. So that's something that if you can come in during lunchtime, not after school today, lunchtime today or lunchtime or after school tomorrow. If I can grab a whiteboard and just have like 5 minutes of your time, I'll be able to show you pretty well, okay? But that was an activity that we worked on Friday. You probably heard it in the YouTube video, but it might have been a little bit harder for you to see. But I can use this one example right here. Let's go ahead and use the notes. Guys, the notes I think I showed a little more work in, right, than the homework problem. Where's a good one that we could show them where I showed good work? Here we go. This one's not too bad, right? This one's not too bad. Jason, can you walk me through the solution and let's see if Friday. So multiplying, where did we start?
You start at the top left term on the first equation, on the second.
Mm-hmm.
You multiply those two to get you -2, and then you go over with your left hand and down with your right. Multiply those two and add it. And then you go over again and down, and then multiply those two and add it. And then the sum of those three would be the first number. And then for the next part, you go, you switch down or over. Yeah, you go over to the second and do the same thing. Go cross over. Yeah.
So 403.
Yes.
Good. And those combine to be
7.
mm-hmm. Then what?
Then you would go down with your left hand and start with that row, and then go back to the first column. Do the exact same thing. And then with the second row, you would then, and then you would go over to the second column and do the exact same thing.
So it's a constant series of working your way across is what I have in the notes, and down. Working your way across and down, corresponding the entries, multiplying and then adding, and putting it all together. And one way of keeping track of it, maybe some of you, maybe you would appreciate this a little bit more now that we've practiced it a lot. Remember how at the very beginning of this chapter, I showed you guys the notation for the terms, right, in a matrix? Well, how did I know this was going to be a 2 by 2? How can I already start with that assumption? Yeah, this shows the order of the solution. The inners have to match to make it legal because I have to be able to correspond when I go across and down. And then the outers show the size of the resulting matrix. But I'm going to use first row, first column. And then to get here for my answer, first row, second column, first row. So there's another way, or here is another way to keep track of what you're doing each time you're doing this process. Second row, first column. Okay, second row, first column. So once you get in the habit of it, Matthew, you kind of just move without even really thinking about it. But if it helps, you can think, okay, to get this part of my 2 by 2 answer, I'm going to go across my first row, down my first column, across my first row, down my second column. And as Jason was saying, we match up multiplying, plus multiplying, plus multiplying. Whole first row, whole first column, put that together to get first row, first column answer. You can practice a little bit more if you're able to come in with a whiteboard, and it might help because I literally had them in groups. We were working on it, 3 different problems, so everybody got a chance with the whiteboard, and we were talking it out, and so they were able to really, really experiment with it until they were able to get more solid. How many of you guys in homework were still able to do the multiplication over the weekend? Like you remembered it, maybe had to review a little bit. Good, the majority of the class. So that gives you at least a little bit of a view, Matthew, but we can go a little bit more in depth if you have time to come on in. All right, however, sorry, I don't want to just stop there. Was there or are there any other questions in homework, Priscilla? Yeah, 69. Anything else besides 69? Okay. 69, I think I have the book right here. Let me turn on the light though. What were the directions in 69? Talking about LCD TVs and warehouses. Now, unlike the example that we actually, someone wrote in my book. Anyway, unlike the word problem that we actually didn't have time on Friday because we were working so hard on multiplication, the example in the notes that we had to skip actually didn't have any labels on, is this direction, didn't have any labels on their matrices, but the book was really nice in that they showed us, hey, warehouses are the columns, first warehouse, second warehouse, and the models are the rows, which is kind of given in the information up above because it talks about how there are 3 TVs and 2 warehouses, so there are 2 columns and 3 rows, so maybe we could have done that on our own anyway. But it talks about the prices per unit are represented by the matrix, compute B times A and interpret the result. I think I'm just going to do that over here if you guys don't mind, since it's on the YouTube video. And what is this person, whoever had this book a few years ago? I guess I could look up their name, but anyway, I won't call them out right this second. what were they doing right here? Yeah, they were just seeing if it was legal, right? So if we do B times A, we're multiplying this whole matrix, 699.95. That looks like a price of a TV, right, guys? And then we have 899.95. And then we have 1,099.95. It looks kind of like, you guys know, well, even with phones and whatnot, that there are cheaper models and more expensive models, right? When we're talking about like series of things. So we're talking about like a series of TVs and probably the lower model, the mid model, the high model. And we're multiplying matrix B by matrix A. So this person was saying, okay, I have a 1 by 3, and then even though I don't agree with them writing in my book, but this was good that they were matching this up, and it is legal, right, guys? Okay, so I have my 1 by 3, I have my 3 by 2, and it's totally legal because those insides match. And what will be the size of the result?
1 by 2.
Okay, it's a 1 by 2. So I have my prices. Oh, I need to go ahead and grab my 5,000 TVs and 4,000 TVs, and they said this was model A. I wonder if that's the cheaper model or the more expensive model. I guess we'll figure that out in a second. That's warehouse 1 and 2. Then I have model B and I have model C. So I have a total of 9,000 model A TVs, but they're just split up. I have a total of 16,000 model B TVs, but they're split up between the different warehouses. And then I have a total of 13,000 model C TVs. Can you guys tell how much the model A TVs are just by the basis of the placement of these numbers in these two matrices? How much are model A's? They're the cheaper ones. They're $700 because check it out. When I go to do my cross down, doesn't $699.95, doesn't that match up with the first row? And so how much are the version B? 900-ish. And then how much are version C? Yeah, so we can tell that each of these are the prices of the TVs. So what happens when we do the matrix multiplication and we multiply those two? Yeah, because if you guys realize what Joe's saying, we're going to get two different prices. We're adding money together. We're going to get two different totals. One total is going to be all the version A's value plus version B's value plus version C's value. So that's going to be the total value of merchandise in warehouse 1. And then when we go cross over down, aren't we going to get the total value of A's plus B's plus C's? We're going to get the total value of merchandise in warehouse 2. And the cool thing is, I mean, you guys could have done this by hand using your calculator, right? 5,000 times plus 6,000 times plus 8,000 times and gotten that value. Or couldn't you theoretically, with a word problem and with decimals, guys, I would let you use your calculator. So if you're using your calculator, how else could you use your calculator in this problem? Create two matrices, exactly. Your 1 by 3 and then your 3 by 2, and you could just multiply them. But they did say explain the result, right? Interpret the result. So it's the total merchandise in each warehouse. And we could technically add those two together and get the total merchandise. But right now, the answer matrix is the total merchandise value in 1 and the total merchandise value. We could say the total inventory if we're talking about value in warehouse 2. Does that kind of make sense? Cool. Cool. All right, Priscilla, that's good. And then just throw it in your calculator to solve. All right, anything else from homework? Going once, going twice. You guys can get your notes open to section 8.3 and get ready. 35? Thanks, Joe. 35 was a matrix multiplication. Were you trying to do that one by hand, bud? Oh, okay. As I look at number 35, we just have to remember which one's which as far as rows and columns, right? So matrix A is, I shouldn't do equals, I should do like a colon, is a 3 by 2. And matrix B, yeah, exactly, good. 3 by 3. So if we were matching that up, I'm going to say impossible. Your calculator would say dimension mismatch or something to the effect of dimension is off because the 2 and the 3 don't work. And that also works if we were to try to do our cross down. Wouldn't we run out of columns on the first one? Yeah. So good, Joe. That is an impossible one. Nicely done. Yeah.
I don't know if I missed it, but did we ever grade 8.1?
Did we not? Can you guys double check and make sure you have colored pens? Did we grade 8.1? I think we had multiple people that say maybe we didn't. That's weird. All right, let's grab out our homework spirals. I don't want you guys to lose points on 8.1. I have some. How many of you guys have colored markings on 8.1, like you graded it with us? Oh, yeah, not very many. All right, let's go ahead and do 8.1 fast. Sorry, guys. That's my bad. Thanks for asking, though, Priscilla. Oh, yeah, no, we totally didn't talk about the zoo. Did we? I don't think so. Okay. Section 8.1. I must have gotten distracted with, oh, that was the day I was gone, and you guys were sitting, yeah, okay. Got it. Got it. Yeah, we got a little confused with Miss Duck. Okay, here we go. Section 8.1. Reduced row echelon form, or RREF. Number 12 would have been a 3x4. That's the order. Number 20 was super nice and easy. It was just writing the augmented matrix, and that's it. All they wanted you to do was write it, which is pretty cool. Number 46, they were asking you to identify if it was in row echelon form first and then reduced row echelon. It's not in reduced row echelon, because reduced row echelon, if I have a 1 in a row, I should have zeros everywhere else. And so since I do, that guy should have been a 0 to be an RREF. But row echelon says as long as you have 1s and 0s, you're good. So I didn't really care if that guy was there. And that's that dotted line extra column, so I don't even worry about him. So row echelon, yeah, 1s and 0s. Reduced row echelon, nope. Nope, nope, nope. Number 52. Did you guys notice, even though it didn't make you solve, that 52 was weird? Yeah. You were allowed to use your calculator, RREF, but, whoa, 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 whoa. 1 zeros, what's missing? It's because it was impossible. So that's a little tricky. Now, this one doesn't have a 4th column, so since it doesn't have a 4th column, we can't see like what the answers would have been. So they're not making you do like let z equal a, but we would have had to do something like that as far as solving. But in this one, ironically, it's one of those weird, if we did have an extra column, if this did show a system of equations, we'd have to let, actually in this one, we'd have to let y equal a, because he's the one that's missing, that 1 in the middle column. But anyway, yeah, not every matrix can go all the way down to reduced row echelon form. Number 58, there were a few different ways to plug and chug, but basically a back substitution seals the deal, so you can solve that one pretty fast. Number 78, they had you do the system into a matrix and try to RREF, but what happened? Okay, so what do we do whenever we get a row of zeros? Yeah, except this one was only a 2-dimensional system. So it's not z equals a, it's the guy missing y. Good, good, good. Let y equal a. And then back substitute into your little first equation of x minus 3y equals 5. You were able to get partially there, but then he cancels out. So it's like, all right, fine. Y equals a. Plug and chug. Back substituting, you can end up seeing that x would be 3a plus 5 when you simplify. Number 12 was a nasty one as far as decimals, but the nice thing is with it being in decimals, you could have done it by hand, but only after you got rid of the decimals. Some of you might have done RREF in your calculator because it was like one of those word problems at the end, assuming that I would let you do that. I wouldn't be totally against that because most word problems you would be able to use a calculator on. But if you were trying to do this by hand, if I were you, I would have multiplied each of these decimals by 100 and gotten rid of all those decimal places. You would have gotten 8x plus 9y plus 12z is 18,600,000. And then you could have done row echelon form. But you had to use the words. And this was the zoo borrowing, right? Yeah, this was the zoo borrowing money to add up to $2 million is what they needed. They weren't able to get the full $2 million at these lower interest rates. So they took out as much as they could with the 8%, as much as they could with the 9, as much as they could with the 12. All three loan amounts had to be the $2 million that they were taking out. You had your interest, they told you was $186,000. And they said something like the amount in the 12% is double the amount in, or was it backwards? The amount in the 8% is double the amount in the 12%. So you had to kind of make your own equations, get them all moved to one side with your x's and your y's and your z's. And then you had your matrix that you could row reduce to get your final solutions of z is equal to 600,000, y is 200,000, x is 1.2 million. So if you wanted to do it by hand, get rid of those decimals. And if you're using RREF in your calculator, I understand it was a word problem. I would have probably assumed that too. Well, no, I would have been a nerd and I would have done it by hand. But I understand how you could have come to that conclusion. All right, any questions on 8.1? Yeah.
Under 31, I understood that the line was too switched, but I didn't know how to get it.
Okay. Were you trying to do RREF in that one? Oh, and it showed you like how, right? Got it. So, 31, right, Priscilla? Yeah, I see the R1 switched with the R2 because they wanted that -1 on top and that 0 on bottom. They probably should have multiplied everybody by a -1 first to get that nice established 1, but for some reason they just tackled that 0 as was. So to tackle that 0, the only way we can get rid of that 4 is if we add the opposite, right guys? Yeah. So then they must have multiplied, I guess it would have been the old R2. They must have multiplied where that 1 was. They could have multiplied by a +4 because there's a -1 there, huh? So +4 could have been multiplied by this guy and then added to row 3. Once again, I wouldn't have done it quite in that order, but let's see if that works. So R1 and R2 would account for both of those guys, and 4R2 plus R3 should have accounted for that. In that 4 times -1 is 4 plus 4 is 0. 4 times 3 is 12, minus 5 is 7, -28 plus 1, 24 plus 3. Got it. Does that make sense, kiddo? Yeah. So they did it in a little different order than I would, but that's how they did it. Anything else? 8.1? Okay. Whew. Finally, we're caught up then. Sorry, guys. That field trip last week messed us up in a couple ways. But now we're finally able to get back to Chapter 8 and get into Section 8.3. I'm going to delete this word problem because the one from homework I think was better. And it was nice and labeled, and we were able to understand the meaning of it a little bit better too. So we'll just move on past that example to Section 8.3, inverses of matrices. Inverse, it's an idea that you hear a lot in Pre-Cal. You heard it a little baby bit in algebra, a lot more in Algebra 2, but then even more in Pre-Cal. Inverses. So before we got to matrices, let's go before matrices. Let's see. Inverses. If I had something like the cubed root of x minus 1 equals 5 and we needed to solve, or if I gave you something like 3 ln of x plus 1 equals 9, or if I gave you something like sine of 2x is equal to 1/2. Why am I writing all three of those underneath the root portion of inverses? What do all three of those equations need to be solved, guys? Inverse operations, yeah. All three of those would need inverse operations. So before we even get to inverses of matrices, just a quick reminder of inverses. They undo things, right? And we've talked about lots of inverses this year. Now, we haven't really mentioned it. I think I have, but I haven't made a big deal about how addition is the inverse of subtraction or division is the inverse of multiplication. I mean, I talk about it, but it wasn't like a huge point this year. So even in this one, the inverse operation, I don't think I've made a huge deal about it, even though you guys should know. How do I undo this cubed root that's trapping in my variable right now? What's the inverse operation of a cubed root? Yeah, a cubed power, right? So the only way to get towards the x is the inverse operation of a cubed root, which is raising to the third power. All of a sudden, everything is free. Everything is able to be solved. Now, technically, 5 times 5, 25 times 5 is 125. We would need another inverse operation, because right now there's a subtraction by 1. The inverse addition. So technically, we need inverse operations, but that makes it legal to solve. How about the second one? Actually, I would E, but not yet. Yeah, I need to divide first. So I need to do the inverse operation. Oh, not divide by 9. I need the inverse operation of multiplication, which is division. That was like algebra 1 inverses. You were talking about inverting or undoing subtraction or multiplication, addition, division. But once I get that ln alone, now what is it legal to do? Or now what inverse do I need? Yeah, a base of e on both sides. Because e to the ln, they're inverses of each other, and I end up with that number. I don't know, it's a decimal. But just leave it e cubed. Inverse operation of addition is subtraction, and we end up with x equals e cubed minus 1. If we tried to approximate e cubed, it'd be good for our understanding to realize e is almost 3. I think I heard you saying that it's almost 27. But the exact precise answer, we should just leave it e cubed minus 1. And letter C, what am I going to start off doing? Not the formula. Get rid of the sign. How do I get rid of the sign? Sine inverse. Cosecant has to do with reciprocal. So I could rewrite this as 1 over the cosecant of 2x, but Jason, I think that makes it harder. But sine inverse actually undoes that sign, which gets me one step closer to the x, right? But what I do to one side, just like the rest of this, I have to do to the other. Hey, I'm forcing you guys to review the unit circle at the same time. Sine inverse of 1/2. 1, 2, 3, 1. Pi over 6. Sine counts up, 2, then 3. Cosine counts down, 3, then 2, then 1. Square root of 3 over 3, 1 square root of 3 is tangent. So pi over 6, pi over 4, pi over 3. Sine is 1/2 at the first, at pi over 6. And then the inverse operation. Now I'm not going to stress about coterminal angles and plus 2 pi n, and we're not going to stress about that. Just getting one answer, we would then divide both sides by 2. Dividing by 2 is complicated with a fraction. I'm going to multiply by 1/2. Life is a lot better. One possible answer would be pi over 12. What's in common with all three of these, besides them all being equations and all having an x? They all needed inverse operations to solve. So, matrices, we talked about addition, subtraction, multiplication by a constant, multiplication by another matrix. We're building up. We've seen how they're used for systems of equations. But now it's time to talk about how can a matrix be undone? And maybe not so much a matrix, because a matrix in and of itself isn't an operation. It's just like it's like saying, how can a number be undone? Well, a number just is itself. So maybe it's not how a matrix can be undone, but how matrix multiplication can be undone. Inverses. In a way, it's kind of how a matrix can be undone, but it's with multiplication as the operation. Now here's the weird thing. Inverses only exist of square matrices, and we'll see that a little bit more as we go into today. There are not inverses of non-square matrices. We'll see why. But it kind of comes back to the, guys, who's the I matrix again?
1, 0, 0, 1.
Yeah. What's the name of that one? 1, 0, 0, 0, 1, 0. Identity matrix, the identity matrix. Do you remember how from section 8.2, the basics of matrices, identity has to be a square matrix? So that's part of the reason why the inverse has to be a square matrix too. You can't get to the identity matrix without using square matrices. And if you realize, this is where it gets crazy. Didn't we say A times B does not equal B times A? Or did I say A times B does not necessarily equal B times A? Because there is a special case where A times B will be B times A, but only when you're multiplying a matrix with its inverse or an inverse with its matrix. And in order for multiplication to work both ways, it has to be a square matrix. Because only a 3 by 3 times a 3 by 3 will work either way. Only a 2 by 2 times a 2 by 2 will work either way. So there's a few reasons why only square matrices can be inverses. But if you guys notice, how can we tell if a matrix has been undone? Because you're back to the identity. How can you tell if a matrix has been undone? Because you're back to the identity. So just in case, I know we said it out loud, but some of you guys, the verbal things that we go over in class, they sometimes get lost. Just a quick reminder. I is the identity matrix. And I think Joe was the one who was actually reminding us of what those identity matrices look like. We keep going, right? Ones and then zeros elsewhere. And I could, just kind of depends on the size as to, anyway, keep going in every direction. But identity matrices will be those n by n square matrices. Now, in this section, just a quick heads up, we're going to see a lot of different ways of doing square matrices. Some of you might like one way over another. And depending on the size of the matrix, let's just say for little baby 2 by 2s, there's a lot of different ways. But for 3 by 3s, there aren't as many ways, sadly. So let's figure out, first of all, even just whether or not we can recognize an inverse. Looks like all the numbers just kind of got swapped around. Yeah, I asked whether or not they're inverses. Why is Joe telling me to multiply them? Because what did we just see about inverses? When you multiply, what happens? They cancel out to the, not to the 0 matrix, not to the 1 matrix, but to the identity. So Joe's saying B times A, but then also, couldn't we be doing A times B? Because we just saw it has to be true either way. So I don't know. These first 3 rows, you guys do B times A, and then you guys do A times B. And let's see if they match. I'll do both just because I'm snazzy like that. Teacher should do double the work, right? Wait. All right. Multiply the way you're supposed to be multiplying. And then we'll compare. Get to practice our multiplying skills all at the same time. But you guys notice with the 2 by 2s that these are both legal to do, right? They're legal to do, and you get a 2 by 2 for an answer. -1 plus 2. I don't know about you guys, but I think I'm getting 1, 0, 0, 1. This side of the room, how do we get identity? That side of the room? Identity. Sweet. Either way you went, A times B or B times A. They ended up getting the identity, therefore, yes, they are inverses of each other. So when an inverse gets sorry, I apologize. When a matrix gets undone, the identity is left. When the matrix gets undone, the identity is left. Okay, that's just how we recognize an inverse. Let's do a little bit of vocab, and then we'll talk about how to find at least one or two ways today how to find inverses. So, vocab. Invertible. Hey, we saw that earlier this year. Actually, technically last calendar year, but this school year, first semester. Invertible. Convertible. Able to be converted. Kind of, right? From a roof over your head to a non-roof over your head. Invertible. Able to be inverted. AKA invert matrix exists. That makes sense, right? Convertible, able to be converted. Invertible, able to be inverted. The inverse exists. A inverse exists. Singular. Well, if non-singular means the inverse exists, isn't singular going to be the opposite of non-singular? So the ironic thing is singular, the inverse does not exist. Does not exist. Isn't that just D&E? We'll be lazy. There is no inverse matrix. The inverse matrix does not exist. That's probably going to be one of the most confusing vocab things because we're used to a non-word having like a negative meaning. In this case, non-singular. Singular describes an impossible to invert matrix, or a matrix whose inverse does not exist. We already talked about non-square matrices cannot have inverses, so all non-square matrices are singular. However, here's the struggle. Not all square matrices are singular. Ruh-roh. So what are we going to do? Well, we have some different options. Let me just show you guys, as the bell is about to ring and you're packing up, totally fine. Just let me show you one way. One way is going to be a little baby system of equations where I'm going to finish so that some of you guys might be able to get started on homework tonight, where we can do our multiplication and say, hey, you have to be 1. Ta-da! And we keep on going and get little baby systems and solve them for A and B and C and D, but we'll find more tomorrow. Get out of here, cool kids. Tonight might be a non-math homework night. Make sure you have 8-1, 8-2, totally done, caught up. Maybe other homework tonight. Save 8-3 for tomorrow. Bye.
Are we going to get our test back?
Yeah, I meant to today, but we ran out of time with 8-1 questions. Remind me tomorrow, okay? Good morning, bud. How you doing?
I have no clue what is going on.
But rest of homework besides 10-1? Was it?
It was okay.
Okay. Lagrange.